Welcome, denizens of space-time. I hope you can hear me okay. This is the second or third in our now erratically but semi-regular AMAs. In this case, however, it's, I guess, an AMAA. Ask me almost everything. We polled you to ask if you would prefer that we do a topic-focused AMAA or a true AMA, Ask Me Anything. The poll lasted for a few days, and I think there were maybe 10,000 responses in the end, and an exactly 50-50 split. One thing we didn't ask is whether you wanted us to do this at all. So we're just going to assume that every single one of those multiple choice answers wanted us to proceed. To try to keep you happy, we decided to do a topic-specific AMA, but one that is as general as possible. In fact, that covers the entire scope of this show, space-time. And so the topic for the day is the nature of space and the nature of time. Now, I should start out by pointing out that no one knows what the nature of space and the nature of time are. And so forgive me if we don't get any real answers by the end of this, but it seems appropriate to start with a quote from someone who isn't perhaps an expert, but does perhaps have the wisdom to guide us. In fact, a question from Examinarian gave this quote: "Time is an illusion, lunchtime doubly so." Of course, from the late great Douglas Adams. And if we're using Douglas Adams, we might as well go for the most famous Douglas Adams quote on space, which is simply that space is big, really big. You just won't believe how vastly, hugely, mind-bogglingly big it is. And that's about all we know about space and time. Time may be real, it may be an illusion. Likewise, space, although if it's an illusion, there's certainly lots of it. I'm probably not more qualified than Douglas Adams to expound on the nature of space, but I'm sure going to have fun trying by answering the questions that you guys posted in the community section on YouTube. So following his quote, Examinarian, forgive me if I don't get all of the names right, asks, simply, what is the nature of time? And why does lunchtime run at different speeds for the patrons, waiting staff, chefs, and the lad who empties the bins? On the same note, Cosmic Insane asks, what is space? What properties does it have? What can we measure or derive, etc., etc.? So before launching into some of the more detailed questions, and there are many very good ones, I want to muse a little bit upon these topics to sort of flesh out what we're actually pursuing here. So I guess we have a spectacularly successful mathematical description of both space and time. Okay, we start in this description with Newtonian physics, in which the dimensions that form the stage on which the play of the universe takes place. In the case of space, it's the coordinate system, it's the grid on which particles move, they exert forces on each other. And then, of course, we have time as the series of stages, okay, the pages of the flip book, in which the particles' positions are updated due to all of our beautiful Newtonian mechanics. Then Einstein came and changed all of it. Space and time became space-time due to the fact that these two dimensions have the tendency to morph together depending on reference frame. The best place to explore that is the episode we did on the geometry of causality. But I suppose still space and time remained a type of stage, albeit a very wibbly wobbly morphable stage. The big difference is that it became impossible to define a single spatial stage, a single slice of space, as some kind of definite now or universal simultaneous moment. The relativity of simultaneity showed us, I guess, that my perception of now could be some other observer's future and yet another observer's past. And this leads us to the notion of the block universe, okay, in which all space and all of time, they sort of have a unified, timeless existence. The appropriate episode is, of course, do the past and the future exist? But even with this block universe, it's still, in my mind, kind of like a stage, okay? It's just now a stage that all exists at once, in which we're defined as winding world lines through this this stack of time slices that can take on different slopes depending on how fast you're moving, on whether you're in a gravitational field. But this depiction of space and time has both of these dimensions as continuous, in that you can subdivide space infinitely, to arbitrarily small pieces, and same with time. You can divide the second with no limit, according to the mathematics of relativity. But I think most physicists now think that we need more than this, partly because we know that space and time simply can't be smooth and continuous indefinitely all the way down. There's this smallest possible size, the Planck length, a smallest possible duration, the Planck time. And we know this because general relativity and quantum mechanics come into impossible conflict below these Planck units of space and time. And the physics just don't work anymore. And so that I think brings us to the question that I'm most interested in, and probably a lot of you are most interested in, is really, what are the building blocks of these dimensions of space and time? And very brave efforts to try to figure it out. The emerging generations of theories of quantum gravity, theories of everything, some of them try to answer this. String theory doesn't. String theory assumes that that the stage is there, that the space and time, all 6 to 11 dimensions of them, depending on which flavor of string theory, exist a priori. But other efforts, for example, there's loop quantum gravity, which imagines these highly abstract connections between these more fundamental entities, which themselves are definitely not space-like, but in their connections, space emerges. You can the episode on quantum gravity, an episode that we haven't done yet, but that I'm working up towards, is on Stephen Wolfram's cellular automaton-based theory in his physics project, in which space and the laws of physics emerge from connections between points in a graph that have rules of interactions between them. Okay, and according to Wolfram, the kind of the smoothness of the dimension of space can emerge naturally from discrete subsets, very, very discrete, more fundamental elements. On the other hand, in Wolfram's proposal, time itself remains time-like. It's the rate of updating of the graph, if you like. And so when we get down to these levels, to some of these proposals for an origin of space and time, although Einstein brought space and time together in a way and meant that they were both dimensions in their own right, it's very hard to keep them that way. It seems that space and time separate in quantum mechanics. Time plays a very different role than space, particularly in the original inceptions of quantum mechanics, and in these other ideas of string theory, in Wolfram's idea, loop quantum gravity, and others. So I hope that is a sufficiently meandering way to convey that we don't know, but some people are making some very brave efforts to figure this out. And maybe as I answer a couple more questions, we can tease out some slightly more satisfying ideas about the nature of these strange dimensions. By the way, I wish I could cover your questions in the chat. There's a good chance I won't be able to, because they're rolling pretty fast. But some of them are hilarious. From my own experience, I can't just read them right now. If I have a moment, I first need to get to the ones that were posed beforehand. So let's see. Let's get to a question. Start with space. Okay, so time is in space the weirder one. So let's get to space for now. And there are a few who are interested in what it means for space to expand or to stretch. For example, in reference to the expanding universe, Li Wang asks whether there's a difference between the notions of expansion or stretching, or space being created, or things just moving apart through space. So for the first of those, expansion, stretching, or space being created in the expansion of the universe, the answer is no. They're always to think about the same thing. The expansion of the universe, described by the Friedmann equations, is it's described mathematically as the growth of something called the scale factor, which is just a multiplicative factor that essentially we can think of as increasing the grid, the size of the grid of space over time. Okay, as the scale factor increases, some imaginary grid that defines what a point in space is expands over time. So in that sense, the points of that grid are getting further apart. And in that sense, we can think of space as being stretched. If space is the grid, then it is stretched. But because space, as far as we know it, is infinitely stretchable, then once we've stretched the grid, we can just draw a new grid between the expanded points. And as far as we know, we can keep doing that. Then that new grid expands and draw a new grid inside it, and this can happen forever. If the ideas about cosmic inflation occur, then it happened an enormous number of times, 10 to the power of 60 increase in the size of the universe over a tiny fraction of a second at the Big Bang, which makes space pretty darn stretchable, I would say. And so, in a sense, because when we stretch the grid, we can draw a new grid inside it, it's fair to say that we're creating new space in a sense, in the sense that new space has the same vacuum energy density. The old one has the same kind of behavior of virtual particles. It has the same amount of dark energy, critically. Okay, the density of dark energy is added every time is a constant. Okay, it's like you're adding more dark energy every time you add a new grid inside. So in a sense, that's a perfectly valid way to think about it. Now, astronomers don't like to think about the expansion of the universe as of objects physically moving through space away from each other, because that would imply that the universe is expanding into more space, whereas we need to think of all of the universe expanding, not into anything. However, observationally, there's absolutely no difference in the effects. And actually, this gets us to another question by Ritam Dutta, who asks whether time dilation and length contraction applicable to objects receding, moving away from us in an expanding universe, works the same way as objects moving relative to each other, okay, due to their velocities in special relativity. Okay, so the answer is that the two types of motion are indistinguishable. The motion of two galaxies moving apart because they're pinned to a space that's expanding, they will see each other in the same way as though they were just moving through space at that same apparent velocity, the same change in distance over time. And as an example, we have cosmological redshift. Okay, so a photon of light traveling from one galaxy to the other has to travel through an expanding space. And in the process, that expanding space stretches out the photon, okay? Increases the difference between its peaks and troughs, increases its wavelength, okay? Decreasing its energy, redshifting it. But if we calculate what redshift would be if, for the case of a galaxy that's simply moving away at the same speed, moving through space rather than with space, and we account for what we call the Doppler shift, which is the stretching of a wave, be it light or sound, emitted by a moving object, simply because if you emit a wave and then kind of are moving back away from the wave as it moves forward away from you, you can stretch out the distance between the peaks and the troughs of that wave due to your relative motion. And you've all experienced that when you've heard a siren on the street change its pitch as it moves past you. So you get the same answer. And so it's not even clear that it's inaccurate to think of galaxies as literally moving away from us versus being trapped in the flow of space, because the two are completely distinguishable. Now, on the stretching of space in a gravitational field, Aditya Gupta asks the following. When we say a large mass bends the space-time fabric, what exactly does the fabric bend into? Okay, I like this one a lot. So probably you've heard the analogy of gravity as being like a dip in a rubber sheet. When you drop a heavy weight on the rubber sheet, it pulls down. And so objects will follow curved paths as they try to pass the dip rubber sheet, where that rubber sheet is an analogy for the fabric of space. Okay, so gravity also curves the fabric of space. So it's not a great analogy in many ways, because the stretching of space in a gravitational field is only a small part of the source of gravity. The more important part is the stretching of time. And of course, we did an episode on that relatively recently. But that said, space in a gravitational field really is stretched, okay, in that there's, if you were to define a sphere around the massive object, that sphere would contain more space. It would have more volume than an identical sphere in empty space. Okay, so in a sense, more space is created in the gravitational field. Space is stretched. The pulling down of the sheet represents something meaningful. It represents something like the space-time grid being compacted to a higher density inside that region. There are more meters per old meter than in the absence of the gravitational field. Now, the other problem, though, with this analogy is that the rubber is that there's an extra dimension into which the sheet is being pulled. Okay, in the case of the rubber sheet, it's the down dimension, okay, the third dimension for that 2D sheet. And so if we're going to misuse that analogy, back to the 3D space and gravity, then the stretching of the 3D sheet of space by gravity implies a fourth dimension into which that space is being pulled in our 3D universe. It's not particularly good to think about it. There is a sort of degree of freedom that you might consider being like a dimension, but it's not a dimension in the sense of the X, Y, Z axes. It is the degree of freedom is the curvature of the space itself. The density of the lines in the grid. So maybe a better way to do the rubber sheet is to pinch it inwards rather than to pull it down. I hope that's helpful because thinking in 4 dimensions is difficult for me. And it's really key to highlight here is that all of these descriptions, interpretations are kind of stories. They're ways of visualizing the math, and one story is typically not the unique and only way to do it. So, for example, you can equally interpret the inward pulling nature of gravity, and other than being due to the stretching of space and time, being due to an inward flow of space. There's a way you can interpret, for example, the Schwarzschild metric, which describes the shape of space around a spherically symmetric massive body, as being a literal cascade in the fabric of space downwards towards an accelerating cascade downwards towards that body. And it's, if you do it that way, you get the same results for the force of gravity, etc. But it's a different picture. It's a different story. It's in some ways it's a more colorful story, but thinking of gravity as a changing in the flow of time gets you a story that gives you the same answers. And we did a recent episode on how it is that the slowing of clocks as you descend into a gravitational field actually causes our experience of force of gravity. So that's one to check out. But again, these are stories that we lay onto the math, and it's hard to say what the core reality really is. And I think, in fact, the core reality to be equally all of them. Okay, it's already 5:25, and since we're running out of time, so let's see if we can learn a thing or two about time to make those 5 minutes stretch for longer than 5 minutes. So I have a question from Shrum, which is that if there's a metric to determine the flow of time that is other than entropy, okay, so by that they mean a way of defining the arrow of time, the direction that time flows forward rather than backwards, that is not entropy. So is there such a one? And if the arrow of time is entirely defined by the direction of entropy, then does a local decrease in entropy, even if the entire cosmos is increasing in entropy, does a local decrease in entropy potentially reverse time locally? So this is really a mind bender. So I'd say that in the block universe view, entropy seems to be all you need to define the arrow of time, which is that things were more ordered in the past and will be less ordered in the future. And while the laws of physics don't care about the direction of time, okay, so Newton's mechanics, even the equations of relativity, even the Schrodinger equation in quantum mechanics doesn't care about the direction of time. They run equally forwards or backwards, so they don't have an arrow of time built in. But we have this fact about this universe, that the universe has a certain boundary condition that breaks the symmetry of time, and that's simply that things were more ordered in the past. Okay, in one direction, from our current perspective, things were more ordered, and that is to say that at the Big Bang, entropy was very low, and in the future, entropy will be very high, and that breaks the symmetry of time. But that's a universal symmetry breaking, and we know that entropy can occasionally fluctuate on small scales. So there's a good reason to think that that the arrow of time doesn't flip in regions where entropy increases locally. I guess to play that out a little bit, it's better to think about entropy in terms of quantum entanglement, okay, which might be the first time quantum entanglement ever clarified anything. So we have an episode on how entropy comes from entanglement, but and we also have an episode or a couple of episodes on how this plays into the arrow of time. So in short, if I recall, the universe started out in a low entropy, but also an uncorrelated state. Okay, so nothing new about anything else. The particles were no particles were entangled, or there was very low entanglement. Okay, so it's like you created all the particles; they only knew about themselves. And then, as we move forward in time, entanglement increases as particles interact. Okay, as particles interact, they become quantum entangled. For us, we can just think about that as they learned about each other. They gained information about each other's existence. So over time, it increases, and then the universe eventually gets to a state of maximum entanglement, which means maximum entropy. And so you can see how any one part of the universe, like you can imagine a small chunk of the universe moving, in we consider the forward time direction, gaining information about the rest of the universe as it moves on. As it moves on, a particle might bump into it and bounce away. Before that happened, it didn't know about that particle. Afterwards, it did know about that particle, entangled with that particle. Maybe there are dangers to that part of the universe that record that interaction. So we can sort of think about that sort of local increase in entanglement. Every small part of the universe, as moves in the forward time direction, becomes increasingly entangled with larger and larger regions of the external universe. And that doesn't happen in the opposite direction. If you rewind time, then every small part of the universe starts out entangled with the rest of the universe, but rewinding time, it then loses that entanglement, it loses information. So if we think of that part of the universe as a brain, then the information thought of as memory. Okay, so we can see how our mental record of the universe, our mental record of the ordering of time, can only evolve in one direction, in the direction in which our entanglement with the outside universe increases. And that's how I think about the fact that we remember the past and not the future, which, by the way, is the name of the episode that you should watch for a much better and delightfully animated explanation of what I just said. But then we just have to think, what is our own personal perception of time? Okay, we exist, our conscious experience exists in the instant, but that conscious experience contains shadows of what has happened in one time direction, but not the other. You know, in any one instant in time, at least the way I tend to think about it, the universe is time symmetric. The future and the past are the same, except that we remember the past. And in the next time instant, we remember remembering the past, and so on and so on. And so we construct this thread of memory that feels an awful lot like an arrow of time. So maybe if entropy did reverse locally, and somehow started out with a memory, but then vanished due to the event that caused the memory happening, some weird fluctuation by chance, then maybe that would feel like time was going backwards, but it's a terribly unlikely, and so in the statistical sum, the arrow of time goes forward a lot. Okay, so I will bring this together with a question connecting space and time, which is to say the speed of light, which obviously defines the minimum time that it takes two regions of space to be connected. And two of you, David Feenstra and Kenny Bradley, asked this question, which is that might the speed of light have varied over time? So the answer is possibly, but it might not have made a difference, and also it might be meaningful to think about the speed of light as varying. So let me see if I can play this out. I have trouble wrapping my head around this one also. So I mean, the speed of light is defined to be a constant in relativity, and it is just one of the starting axioms of relativity, that the speed of light not only is invariant to all observers, but it doesn't change over time. And of course, relativity is insanely, wildly successful, including using it in the equations of special and general relativity in all parts of the universe, in deep gravitational wells, in the distant past, for objects that we see in the distant past, and it works, which is a point in favor of all the axioms behind relativity, including the constancy of the speed of light. It is, however, possible to model the expansion of the universe and cosmological redshift as being, rather than expansion, but as being due to a change in the speed of light. And the great astrophysicist Robert Dicke tried to do this. This is the guy who was just about to build the machine that would have detected the cosmic microwave background radiation before he was scooped by these two engineers at Bell Labs. But he was a genius, and so we should take him seriously. But he came up with a scheme. If you change the speed of light, then it mimics a changing scale factor, a changing size of the universe, and it required some sort of cosmic index of refraction to work. I don't know all the details, but the key here is that the speed of light, really, what we should think about the speed of it is as sort of the scaling factor between the sizes of the dimensions of space and time. Okay, so in the metrics of relativity, for example, in the Friedman, Robertson, Walker, Lemaitre metric, the t component has a c out front, and it's just the scaling factor between the dx, dy, dz, and the dt that defines how big space is compared to time. But if you're a proper cosmologist, you just set it to 1 anyway. And so it's not clear really what changing the speed of light means, except that it doesn't mean changing how big space is compared to time, or how big time is compared to space. And is that meaningful? Well, Robert Dicke found a way to emulate the changing size of the universe by a changing speed of light. sort of makes sense if changing the scaling factor between space and time that could look like the expansion of the universe, but it's not a simple translation. So the if you look at, for example, the Friedmann equations, the speed of light doesn't only appear in such a way that it changes the scaling factor of the universe. It's sort of a non-linear effect on these equations. So it's not as though changing the speed of light is the same as changing the scaling factor. It's a little different. But one thing that is clear is that the speed of light isn't the most fundamental constant. Okay, it's a constant with units, and we tend to think of the more fundamental constants as being the unitless constants. And in fact, by changing the speed of light, if certain other numbers didn't kind of come along for the ride and change with the speed of light, then you might not notice that the speed of light has changed. For example, numbers like the fine structure constant are often considered more fundamental. These are these unitless numbers, and changing the speed of light should change things like the fine structure constant if we're to notice any effect. If the unitless constants don't change, then the simple shifting of your definition of the meter versus the second isn't going to change how you experience the universe, as far as I understand it anyway. It may well be that either the speed of light change or more fundamentally something like the structure constant does change over time. And this is something that astronomers have been searching for quite seriously. Now, of course, we did an episode on it some time ago, in particular the fine structure constant, and it should manifest as things like changing in the detailed energy levels of atoms when you look at the light emitted due to electron transitions in atoms very far away backwards in time. Then potentially you can detect things like changing fine structure constant, which, with the right jiggling of units, maybe that looks like changing speed of light also. But no luck yet. As far as I can tell, the constants of the universe are exactly what it says on the tin, constant. So I think I've got to the end of the questions that I flagged, which were the most popular questions that were not about black holes. And I apologize for missing the many questions that were on black holes. Of course, black holes are about space-time, which you can tell by looking at our playlist and typing black holes in the search and see how many we did. However, if I answered all the black hole questions now, then we wouldn't do an AMAA specifically on black holes, because I would have covered that stuff already. Okay, so guys, this has been a delight. We will do this again pretty soon, if you want. Maybe next time we'll add that third option to the survey. But assuming you click hell yeah, then I certainly enjoy these a lot. And so think about what you'd like me to do. Should I do a general one? I can talk about what I had for lunch. Greek chicken wrap today. It was delicious. Or we can dive into other hairy depths. But this time, probably something more specific than just the general topic of space-time.